Hello, this is like a short description of capacitive transducers. Capacitive transducers are used to convert a mechanical quantity to an electrical quantity or vice versa. In other words, we have a mechanical input or output and we have an electrical output or input. And capacitive transducers are frequently used. I'm using it frequently in my research. Um, For example, accelerometer, we use in an accelerometer, we have acceleration as our mechanical quantity of interest. And this mechanical quantity of interest is then converted to an electrical, say, alternating current. And this alternating current carries the information we are after, carries the information about our measurand, the quantity of interest. And then we process that measurand and the output current, to extract acceleration of the body. So we have attached accelerometer to the body, and this accelerometer generates this signal, this voltage, and we take those voltage, we process that voltage, we deduce what the acceleration of the body is. In general, I'm sure you have already seen capacitors are essentially like this. We have two electrodes and we have a dielectric in a gap. So dielectrics are different materials, and they're mostly just especially in, for example, microelectromechanical systems, we simply have a certain type of vacuum between the two electrodes. So we have air at certain pressure, and mostly it's like very low pressure. So, and the permittivity characterizes the material's ability to transmit or permit the electric field associated with the separation of charge. So you can guess that you can have different materials if your goal is to have if your goal is to change the permittivity of dielectric. So now if you think about it, because we have charge separation, and because of this charge separation and opposite polarities, an attracting force is created between the two plates, right? So as long as I keep these two plates fixed, just like a normal capacitor, nothing happens. But then if we let one of these plates, one of these electrodes move, so have one fixed and one moving, then I can create a transducer, right? So by making one of the electrodes movable, and therefore create a capacitive transducer. Now, the fundamental question is, we know that from basic electronics, that this is how we compute the capacitance between the two plates, between two electrodes. C equals epsilon permittivity, A, the area, and over D, and D is the gap between the two electrodes. Now, the question is how we can change this capacitance, right? Well, one obvious choice is to change the material, so permittivity. But in practice, once we choose our material, we're not going to change it. So the things we could change are area and the gap between the two capacitors, between the two electrodes. So if we change, for example, if the gap goes up, C goes down. If the area goes up, C goes up. So direct and inverse relationship. So this is what we're going to do then. So what we're going to do is, let's say I have made one of these plates movable. Now I'm going to talk about the case where we are changing this the gap between two plates. But you can think about the case where area changes. And I'm going to create another video later sometime and show that. But you can guess that. Let me just point out how it works. So if I start moving this upper plate to the left and right, this changes the effective area between the two electrodes. So it's not hard, but you can guess that this would complicate the mathematical formulation of the problem. But there are advantages in using that. So I'm going to talk about that later. So for now, I'm talking about the case where I'm interested in changing the gap between the two two electrodes. So, and this is the electrical symbol we use once we have this parallel plate varying capacitor. So we have C equals epsilon A over D plus X. So there's no difference in that, right? Because capacitance is epsilon A. A, as I said, we are discussing the case where A is fixed, epsilon is fixed, and D is D plus X. So let's say this movable plate has moved up as much as X. Now our new gap is D plus X. Yes, obviously, if it moves in opposite direction, your gap goes down. So, but it's the same thing. All right, now let me describe this part a little bit differently. So, if you think about a capacitor, a transducer, a capacitive transducer like this case, this is essentially a two-port component, right? So, in other words, how many domains are involved in changing the energy of this component? How many domains are interacting with this transducer, or how many domains is this transducer interacting with? So you can clearly see that we have one electrical domain, so it's because the charge is going to be deposited and stored on these plates, or discharged from these plates. And we also have a mechanical domain because the movable plate goes up and down. So in general, then we have two domains, and these two domains either inject energy into this transducer or receive energy from this transducer. So if I had asked you to compute the rate of change of energy for this transducer, you would say, all right, this is the sum of change in electrical and mechanical energy. It's as simple as that. So the sum of change in mechanical and electrical energy per unit time. And you know that the power in, for example, mechanical domain is like force, and force is an energy differentiated with respect to displacement multiplying velocity of this plate as it goes up and down. And for electrical domain, the same thing. We differentiate E with respect to Q. Electrical displacement is Q. And multiplying I gives us the power, the electrical power, which is either injected into our transducer or received from the transducer. So this is the whole power of this transducer. All right, so now we also know that for a capacitor, energy is half CE squared, and E being the applied voltage to the or the difference in voltage between the two electrodes. So now if you substitute a star into double a star was this equation, the definition of capacitance, into double a star, the definition of energy, you can compute the force, right? So we have discussed two things here now. We have discussed how we compute the force. So because once we let one of these plates, electrodes, move up and down, we have this mechanical force applied to the both plates, one of the plates, but now is moving. So because one of the plates is moving, it's work which is done by the force. So we have computed the capacitance. We have discussed the force applied on this movable plate, and then you can already see that because we have this force, you can really quickly relate this force to your equation of motion. You can, in fact, immediately think of Newton's second law being applied to this movable plate. And then using that, you can think of ways to relate, for example, your desired signal acceleration, output acceleration, to relate to all these quantities. So we have discussed how the energy would change per unit time, or the power. We have discussed the capacitance and the force applied to this transducer. So transducers have many applications, capacitive transducers, and in some later videos I'm going to talk about the case where instead of the gap, the area would change. So we keep the gap constant and then change the area, or you can change both. All right. Thanks for paying attention.